So, welcome back, guys. We're still in Unit 5. Today we're going to do lesson number 2. And one of the things I wanted to go over with you, well, actually three things. Three things that we're going to do today. We're going to explore roots. Once again, the roots of quadratic and all these other polynomial type equations. All right. Now, roots, the things we call roots, solutions, x-intercepts, zeros, these are all the same things. So if I have a graph, let's say I have this curve, right? And here's my coordinate plane. Well, these are the roots. These are the roots. Let's give them a number. We got -1 right here, we got 0 here, and we have 3, right? So if these were the roots, these particular numbers, we would say this is an equation, f of x equals x minus 1, no, x plus 1, it's opposite. This is the factored form, x times x minus 3. So to respect our zeros, we have x equals -1, 0, and 3. And I want you to note that these are the factored forms of these zeros. Those are the factored forms of the zeros. Okay? They're the opposites. So this is a third-degree polynomial. It's a third-degree polynomial. It has 2 turning points, so 2 plus 1 equals 3. Okay? These are the things you should already know. Now today we're going to explore identifying these roots and things like that. But we're also going to touch base on something we call multiplicity. So multiplicity occurs when we have this really narrow turning point here. It may also occur if we hit the x-axis and then bounce back. Okay? So what we've got here is we've got a turning point here and here. This point where you bounce back creates a double root or a triple root or something along those lines. So we're going to explore what multiplicity is, and we're going to look a little bit more at our zeros today. So here we're exploring the fundamental theorem of algebra, which states basically that every non-constant single variable polynomial with complex coefficients has at least one complex root. This includes polynomials with real coefficients, since every real number is a complex number with an imaginary part. So every polynomial has complex roots. Okay? So how many complex roots does the following have? It has 3. How many complex roots does this equation have? Look at the highest degree. It has 5 complex roots. Look at the highest degree for my third one, and we have 4 roots, 4 complex roots. Okay? It's just the total number of roots, the degree of the polynomial, 2 complex roots. Now, also, just before we get started, just keep in mind that roots, when we ask about what the roots are, we're talking about the x-intercepts. We might also refer to them as zeros, and we might even refer to them as solutions. Okay, so below, we're going to just circle where these objects cross the x-axis. It crosses here at -2, and it crosses right here at 3. All right, so if we're going to write the factored form, it would look something like this: x plus 2 times the quantity of x minus 3. My zeros are x equals, curly bracket, -2 and +3, curly bracket. Next one, I have a 0 at -1, 0, and 3. So when I write these zeros, here at 0, curly bracket, 0, -1, and 3. And if you notice, like I said, these are the opposites of what those zeros are. So in conclusion, the last one, I don't even need to really circle them. I can just write them out. For x, for just x, I have a 0 at 0. For 5, I should have one at -5, and -6, I should have one at +6. And for this one, if you swing it back over, it should be 3, +3 over 2. Okay, or 1.5. So if I go through and circle and just check, do I have one at 0? Here it is. Do I have one at -5? Yes. Do I have a 0 at 6? Yes. Do I have a 0 at 3.5 or 1.5? Yes, it's right here. Okay? Don't make it any harder than that. Now, for these right here, we're going to be looking at the number and the type of roots. So remember, when I talk about complex roots, we're referring to the total number of solutions. Okay? So we're going to get the complex roots, total number of solutions, the real roots, and the imaginary roots. So the imaginary roots occur at a point, they occur when it doesn't cross the x-axis the appropriate number of times. So the complex occurs for the degree of the polynomial. It's going to be the degree of the polynomial. The real roots you can count. It's where it crosses or hits the x-axis. Okay? Now, is this polynomial odd or even? So first we look at the end behavior. If the ends are going in the same direction, in a positive direction, you're going towards positive infinity, then this is an even polynomial. If they're going in opposite direction, it's an odd polynomial. For the smallest possible degree, we count the number of turns and add 1. So I have 1, 2, 3, 4 degree polynomial. That means there should be 4 roots, 4 complex roots. Now the number of real roots here is 1, 2, 3, and 4. So there's 4 real roots. 4 minus 4, that means there's 0 imaginary roots. So we're going to do this each time. Okay? So I'm going to go ahead and set myself up here. I'm looking for the number of complex, the number of real, and the number of imaginary. Okay? So let's look at if it's odd or even first. It's going to positive infinity on one side, negative infinity towards the right. So this is the odd polynomial. Smallest possible degree. Count my turning points. 1, 2, 3, 4. The smallest possible degree here is 5. Now, let's count the complex roots here. Should be 5 total. Now, how many real roots? I have 1, 2. So that's 2 here, because it doubles back. 1, 2. So it looks like 5 real roots and 0 imaginary roots. Okay? Looking at the next one, is it odd or even? It's even. The end behaviors, we have positive infinity over here and positive infinity over here. So this is even. This is a second degree polynomial. It's even. Second degree because there's 1 turn. Types of solutions. Well, complex, I have 2. Real, it doesn't cross the x-axis, so there's 0. And then imaginary, 2 minus 0 equals 2. Okay? These are the numbers and the types of solutions that go right here. All right? That was relatively easy, guys. Now multiplicity, I kind of alluded to it. What multiplicity is when a 0 occurs more than once. So here, x minus 3, when x equals 3, that 0 occurs 4 times. So the multiplicity of it is 4. For x minus 5, it occurs 1 time when there's no exponent. X minus 8, it occurs 2 times. So I put a 2 here. So algebraically, it's so easy to tell. Now, the way you tell you have multiplicity is that at the x-intercept, it bounces back. It bounces back. Or you have a turning point. Or you have a turning point. So what's a good example of this particular situation? Right here. It hits the x-axis, bounces back, and there's a turning point there. Okay? The other is when you have this lull, and it's right at the x-axis. There is a root there. It might be a double root, but there's multiplicity in these two areas here. When you see a change, if this is happening at the x-axis, or a bounce back is happening at the x-axis, these three types of situations, you're going to have multiplicity. So, examples of multiplicity. This is an example. It bounces back here, and it bounces back here. Now, this is a fourth degree polynomial. It's a fourth degree polynomial. And we're going to put the degree, d. We're going to put the number of complex roots, the real roots, and the imaginary roots. Okay? So the degree of this polynomial is 4. There should be 4 complex roots as a result. Now you have 1, 2 real roots because it bounces back, and 1, 2 real roots here. So 4, that means there's 0 imaginary roots. So we're going to do this for each one. Now, remember what I said earlier. 2 examples of multiplicity is when there's a lull right at the x-axis, or it bounces back. So this polynomial, it's odd. So the degree of it, I have 1, 2, 3 critical points here. So it's got to be a 5th degree polynomial. The complex roots have 5 of them. So if I have 2 here and 2 here, and sorry, not right there, guys. That's 1. That's 2, 1, 2. So 5 complex roots. The number of real roots is 3. There's a double root where it bounces back. And the imaginary roots, how many I have left, 5 minus 3, is 2 imaginary roots. And we're going to go through that again. So we get to the degree. That gives us the complex number of roots. And then the real roots we count by circling where it crosses the x-axis. So here, the next one, the degree smallest possible would be 3. The number of complex roots is 3. The real roots, well, here it is. 1 time, right? 1 time. And how do you know if the multiplicity is bigger at these points? Well, here it's really, really narrow, but here it's really, really wide. This implies that there actually might be 3 real roots here. But I'm thinking, I'm going to go with that there's 1. I'm going to go with that there's 1 real root, and that the other complex parts would be 2. But typically for a degree of 3, the number of real roots is going to be 3 for this particular instance. And the number of imaginary roots is 3 minus 3, or 0. That was confusing, and I apologize. The next one is an odd polynomial. So it bounces back here. There's 2 roots here. There's 1 right here, right? So the degree here is 5. The complex roots, 5. The real roots is 3. And the imaginary roots, 5 minus 3, is 2. And the rule is you should always have 2 imaginary roots. So which of the above graphs could represent the polynomial f of x? A times x minus b squared times the quantity of a x minus c cubed. And that's going to be this second one. It's B. And I just want to go back through B really quickly because I made a mistake. Here. So I think I was right originally. Okay. Um, So here I have my roots, and it's possible that this has a multiplicity of 2 and this has a multiplicity of 3. So my degree is fifth degree polynomial. Complex roots 5, real roots 5, imaginary roots would be 0. And this would be a good representation of number 6 algebraically. I know that last part was confusing. I think if we go over this each part, we'll figure out where we're going wrong. So things I can tell automatically when I look at the equation of the polynomial. I know the degree. I find the biggest x term each time. So I'm always going to highlight that biggest x term each time, right? Here's my biggest x term, right? That's going to give me the degree. It's also going to give me the total number of complex roots. It's going to give me degree and the total number of complex roots. So the degree is 3. It's third degree. Number of complex roots, 3. Number of real roots, I don't know yet. Number of imaginary roots, it's this number minus that number equals that. All right. But first, we're going to go to our graphing calculators and plug these numbers in, plug this equation in, and graph it. All right. So here's mine. I got y equals, and I clear out my equation in there, right? And so I got, let's look at this equation one more time. X cubed, x squared, negative 4x plus minus 4. So x cubed plus x squared minus 4x minus 4. Let me make sure that's correct. Right? Let's make sure that's correct. X squared plus x, yeah. That's what I have. So I'm just going to trace it and look at it real quick. Looks like there's 1, 2, 3 roots. 3 real roots. That means there's 0 imaginary numbers. So let's go to our table, second table, and see, negative 3, negative 10, negative 2, 0, negative 1, 0. Okay. So 3 real roots. Let's look at it. Negative 2, 0, 1, 0, and then what else do we have here? 0, negative 4, 1, negative 6, and 2, 0. Okay, so my graph looks something like this. Right? So there's 3 turning points. Got my 3 zeros. So there's absolutely 0 imaginary roots. Are there any double roots? No. Are any triple roots? No. Turning points. Now we're on to these questions down here. Turning points. This is a turning point. This is a turning point. There's only 2. This is end behaviors. As it goes towards the right, as the graph goes towards the right, we're heading up to positive infinity. As the graph goes towards the left, we're heading down to negative infinity. Okay, number of zeros, x equals curly bracket. We have 1 at negative 2. We have 1 at negative 1. And we have a 0 at 2. Close the parentheses. Okay? So looking at x to the 4th minus 18x squared plus 81, things I can answer automatically. This is a 4th degree polynomial. That means it has 4 real roots, right? Go to my graphing calculator, plug it in, and have x to the 4th minus 18x squared plus 81. So y equals clear x to the 4th plus 18x squared plus 81. Let's make sure my signs are correct. So I have minus 18x squared, not plus. Minus, right? Go to second graph. And looks like I have a 0 at negative 3, 0. I'm just going to trace it so I can see this more accurately. Negative 3, 0, and at 3, 0. And it's a double root because it bounces back. It's a double root because it bounces back. So have one here at negative 3, and I have a 0 here at 3. And it's a very narrow graph, right? It goes off the map, literally. So 4 real roots. I have a double root here. So the way we take care of that, we want to write 2, but technically it's 4 because of the double roots. So what happens at a double root? That means I literally have x minus 3 squared times x plus 3 squared. That's why it's a double root. There's 0 imaginary roots. Are there any double roots? Yes. There are 2. 2 of them. Are there any triple roots? No. Because typically what we're doing is we're subtracting these 2 numbers to get the number of imaginary roots. But at this point you only have 2 zeros, and I'm going to show you what I mean by the multiplicity. We recognize the multiplicity because it's bouncing back. It's creating a turning point right on the x-axis. So the number of zeros, x equals negative 3 and x equals positive 3. Or it could be written to get the 4, negative 3, comma negative 3, comma 3, comma 3. But much like all relations, when we're considering the domain or the range only, we only write that number once. So technically it's 4 roots, but these are the same numbers, so technically there's 2 real roots and they're double roots. Number of turning points we have here, we have 2. Sorry, we have 3 turning points. In behavior, we're going to positive infinity at both ends. Okay? Moving on. Let's see how many we have left here. Just that last one. So this is homework, guys. This one's homework. I'm not going to go over that. Now, what we're going to do is factor to solve and then check the calculators to do this. So I'm going to sketch the graph using the information that I get from the calculator. But first, for this particular one, I'm just gonna put everything in standard form. So x cubed, and remember standard form, this is gonna move over to the same top side as the bigger term. 25x equals 0. Now I'm gonna factor. I can divide out of x because it's the greatest common factor. So that means it swings out, and I'm left with x parentheses x squared minus 25. Now, for this part, I'm looking for 2 numbers that multiply to 25, add up to 0 in the middle, and I get x times the quantity of x minus 5 times x plus 5. This is a factor form. That means I have a 0 at 0, I have a 0 at positive 5, and I have a 0 at negative 5. Remember, we use the opposites. So to come over to my graph, here's a 0 at 0, here's a 0 at negative 5, and here is a 0 here. Now you want to make sure you're doing this in the right direction, so you might want to go look at the graph, but I'm not going to. But my graph essentially looks like this. Okay? So on one side I have going from negative infinity, the other I'm going to positive infinity. This is an odd graph with 2 turning points. Now if I want to write the factored form of this equation, it's exactly this. You could either write x cubed minus 25x, but the factor form equals x times x minus 5 times x plus 5. So I want standard form and then factor form. Okay? In behavior, as it goes towards the right, we have positive infinity over here. As it goes towards the left, we have negative infinity over here. Okay? Now for x cubed minus 6x squared minus 27x, I can factor out x. There's an x in each term, so it comes out. And I divide each term by x. I get x times x squared minus 6x minus 27. Okay? Now I'm looking for two numbers that multiply to 27 and add up to negative 6. I have x times x minus 6 times x, I'm sorry, not x minus 6, x minus 9 times x plus 3. That's going to equal a 0 at 0, a 0 at positive 9, and a 0 at negative 3. Okay, so I'm going to go put my zeros on the map. Here's one at negative 3, here's one at 0, and although I don't have 9 on here, 9 is over here somewhere. Right? This is a cubic function. It's positive, so it's going to look something like this. That's what my graph looks like, right? Now, in behavior, on the left, I'm going towards negative infinity. So as it goes towards negative infinity, I'm going to negative infinity. On the right, I'm going towards positive infinity. Number of turning points, 2. Standard form is x cubed minus 6x squared minus 27x. Factored form is x parentheses x minus 9 times x plus 3. Okay, so I'm going to let you do number 3 on your own. Remember to factor out those x's, guys. Let you do number 4. And yeah, that's your homework right there. Now, give all zeros of each function, indicate the multiplicity of each zero. So first, the multiplicity of this 0, it's only to the power, is 1. The multiplicity of this 0 is it's squared, so it's 2. So here, x equals curly bracket. For x, it's simply 0. For x minus 6, it's simply positive 6. Okay? And the multiplicities are listed there, right above it. This is a third-degree polynomial. Okay? For the next one, this is a fourth-degree polynomial. Multiplicity of 2 is 1. Multiplicity of 4 is 3. So the zeros will be the opposites. So here, for 2, multiplicity of 1. And for 4, or negative 4 actually, it's a multiplicity of 3 because it's cubed. That quantity is cubed. Keeping that in mind, here I have 3. Well, actually, we're going to do multiplicities. Multiplicities that way. Multiplicity here is 1. Multiplicity here is 1. Multiplicity is 1. Multiplicity is 1. Zeros, x equals 3, 2, 3i, and positive 3i. Right here, multiplicity is 2, 1, 1. My zeros, 0, 1/2, and 9, negative 9/4. So for this last two problems, I probably should do those with you. Okay, let me do those with you. So this equals x, this simplifies to x plus 4i times x minus 4i and x minus 2. There's the multiplicity is all 1. My zeros, negative 4i, positive 4i's, and positive 2. For f, swings over, becomes 6 over 3. Multiplicity here is 1, but the root of it is 2. Right here, this becomes x plus square root of 5 times I times x minus square root of 5 times I. So my last two zeros is 5i, square root of 5i, and the negative of square root of 5i. Okay? Number 6, you're going to do C. I'm going to do a and b. So this is a third degree polynomial. That means there should be 3 complex roots. But the number of real roots is the number of times it crosses the x-axis. That's 1. That means there's 2 imaginary zeros. Here, this is a 4th degree. There's 0 real zeros. That means there's 4 imaginary zeros. Number C, it's a 4th degree polynomial. You tell me the number of real zeros, the number of times it crosses the x-axis, and the number of imaginary numbers. Number 7, I'm not going to do it for you. This is part of your homework. It says follow the model of first 3 examples already done for you. Complete the table below. To fill in the last column, multiply the factors. Things you should know how to do. These are my solutions. These are my zeros. That means there's 2 real roots. This is a quadratic. This is a 2nd degree polynomial. The only thing I'm worried about is when you multiply this in order to get the standard form. So when we're multiplying, please use the box method. So x minus 3, x minus 4. The box method's like this. You create a rectangle. Here's my problem. X minus 3 times x minus 4. Your method here is to put them in the correct places. The first part is going to go x and negative 3. The second part is going to go at the top, x and negative 4. When you're multiplying x times x, you get x squared. Negative 4 times x, negative 4x. Negative 3 times x, negative 3x. We're going to combine these terms. And then, for the last term, negative 3 times negative 4 is positive 12. So what we do is set ourselves up for success. We write it all out. We have x squared, our 2 like terms, negative 3x minus 4x's. And then plus positive 12. Combine these numbers, you end up with x squared minus 7x plus 12. If you're confused, continue to Google or YouTube box method. There's no reason to stop. There's no reason not to look. Do the box method. Now, your homework tonight is on page 19. You have number 4 to do on page this one, 18, and number 6. So homework. Page 17, number 3, number 4, and number 6. So 17 and 18. Page 19, number 7. If you are confused, you need to play back the video. I will see you guys next week.